What you're seeing is a device moving up the tiniest of slopes to the right by accelerating and deaccelerating a revolving mass depending on that mass's position. This effect is very weak, such that the slope is not steep enough to overcome the static friction of the wheels and cause the cart to roll down it in the absence of the masses revolving. You can see that if I increase the frequency of revolution, the cart vibrates its way down the slope. When I decrease the frequency, it slowly climbs the slope. So what is going on here? Well, if you've been following my previous work on this kind of device, you'll know that the dynamics of this simple device are actually a bit complicated. We know via Newton's laws the only way to change an object's velocity is to apply a force to it. Doing so creates a reaction force against whatever is accelerating the object. This is true even if the object's speed doesn't actually change, only direction of its travel. Thus, if you have a mass revolving around a central axis at constant speed, because the direction of its velocity is constantly changing, you create a sinusoidal reaction force along the x and y directions of that central axis. You can cancel out the x-component oscillation by mirroring the system with the second mass revolving in the opposite direction that is perfectly in sync with the first one. This creates a device that can displace itself with an average velocity without having the need to interact with its environment in the same way that something like a car does by exchanging friction forces with a road to move itself, or a rocket that exchanges momentum with its environment by expelling a propellant. In general, if you cumulatively integrate a sinusoidal acceleration starting from zero, you end up with pulses of velocity. The average force acting on the device, however, is zero, thus the device cannot accelerate itself or overcome any kind of external forces impeding its motion. Things are different, however, if you alter the device such that the mass revolves at a speed that changes. Here we have assumed that the speed follows a Gaussian distribution centered on pi/2 with a width such that it accelerates while going up from -pi/2 towards pi/2, maxing out at pi/2, and then deaccelerates coming down the other side, regaining its starting speed at -pi/2. The result is that there are reaction forces from changing the revolving mass's speed in addition to its direction of travel on either side of pi/2 that point in the same direction. This is easiest to see when compared to the reaction forces created by a constant speed revolving mass shown on the right. We can see that changing the speed of the mass has made the oscillation become asymmetric. This means if we integrate the force, it now has an average value. We have to be a bit careful about how we integrate though. We started with an assumed velocity at different positions defined by an angle. But energy, velocity, and force have units involving time. They are not parametrized with respect to arc length. So before we integrate with respect to time, we have to compute at what time each point and its corresponding velocity vector occur. Because we started with an arc length parametrization, time is now a dependent variable, and we can see it progresses non-linearly with respect to arc length. In this setup, I'm using 4 magnets of alternating polarity detected by a Hall effect sensor to provide positional feedback, which is fed into an Arduino to modulate the speed of the DC motors via pulse width modulation. The mass, in this case, is 2 pairs of 2 stacks of 10 Canadian quarters, and it is accelerated counterclockwise from -pi/2 towards pi/2 over an unknown distance. It's unknown because I currently have no way of verifying how fast the motors actually accelerate the mass. The reaction force from accelerating the mass in this way causes the cart to initially move to the right. The centrifugal force now acting towards the left causes the cart to slow and stop. Once the mass gets to pi/2, the speed of the mass is decreased. You can see this happen here in this slow motion video. It seems to finish decelerating at about pi, so a good estimation of the distance for acceleration and deceleration is pi/2 of the disk's arc length. Reaction force from this deacceleration reduces the amount of distance the cart would displace to the left if the mass was revolving at a constant speed. If the direction of acceleration is reversed, we can see the cart now move to the left with a much greater speed since it is now traveling down the slope. In this case, the direction of revolution is the same, but the control scheme has been altered such that the mass is accelerated as it moves along the outer 180-degree arc instead of the inner one, thus causing the motion to the left instead of to the right. What is interesting is that there is a specific range of speeds where this effect can climb the slope and it will go down the slope for all others. Not entirely sure why this is the case, there are several possibilities. The most likely one is that it's because of how I'm deaccelerating the mass. I don't actually apply a brake to the motor, which would be ideal. I simply apply a lower pulse width modulation value to the motor and allow the friction of its internal gears to slow it, such that at a higher base rate of speed it doesn't slow fast enough, making the difference between the high and low speeds smaller. The other, more hand-wavy explanation is that it has something to do with the mechanical impedance of the system. The system as it is now is not perfect, and definitely tends to flex and bend while it operates. At certain frequencies this may interfere with or overpower the desired effect, causing the device to effectively bounce on itself and the underlying cable.